Assalamualaikum and very good day to our lecturer. We will present our project titled Structural Remediation and Digital Twin Engineering for the Hulu Selangor Freight Corridor. This project focuses on one of the major freight transportation corridors connecting the Bandar Sungai Buaya industrial area to the Serendah industrial area. The corridor experiences heavy traffic congestion, particularly due to the large number of heavy vehicles using the road every day. The industrial artery and breaking point. This slide illustrates the study area and highlights why this corridor has become a critical transportation bottleneck. The route connects several important industrial zones. Because these industrial facilities generate a high volume of freight movement, the route serves as the main logistic corridor and transporting goods and materials. However, the existing road network was not designed to accommodate the current traffic demand. As industrial activities continue to expand, the number of heavy vehicles has increased significantly, leading to severe congestion, delays, and operational inefficiencies. Therefore, this corridor has become a critical point requiring immediate engineering intervention. These slides present the traffic condition at several major junctions along the corridor. We can observe that the average traffic flow exceeds the design capacity at almost every location. The level of service, or LOS, ranges from E to F, indicating unstable traffic conditions and even traffic breakdown. During peak hours, especially during synchronized factory shift changes, a large number of trucks enter and exit the industrial area simultaneously. As a result, vehicle speeds drop below 20 km per hour, causing long queues that extend back to the plus highway acceleration lanes. Turning blockade. This slide explains one of the key geometric problems contributing to traffic congestion. The existing junction geometry is not suitable for large freight vehicles, particularly WD-20 trucks, which require a much wider turning radius. Due to the limited turning space, these heavy vehicles cannot complete their turn smoothly. Instead, they can often occupy opposing traffic lanes while turning, creating conflicts with oncoming vehicles. This situation reduces traffic flow, increases delays, and raises the risk of accidents, especially during period of heavy traffic. Therefore, improving the junction geometry is essential to ensure smoother truck movements and enhance the overall efficiency and safety of the corridor.
For our geotechnical subsurface profile, we found 4 layers. Near the surface, soft alluvial clay has almost no structural strength, risking settlement under heavy loads. Below that, weathered granitic soil is moisture sensitive and needs temporary shoring. Deeper layers contain hard core stones that risk obstructing our piling rigs. Since stable bedrock only appears past 35 meters, a standard slab foundation isn't viable. We are designing deep bored piles socketed well into that solid rock. For the accelerated degradation, the existing corridor isn't just congested, it is physically failing. Our pavement condition index has dropped from poor to fair, with deep rotting and cracking from repeated heavy shear stress. The drainage network is collapsing too. 40% of the culverts are blocked with industrial slit, causing flash ponding during monsoon downpours. And the surrounding community is paying the price. Peak noise hits 78 to 84 decibels during shift changes, which exceeds the daytime limits, while idling diesel engines push emissions past national air quality thresholds. Given this complexity, legacy 2D CAD methods can keep up. Manual cross-sections, slow disconnected updates, and a high risk of hidden utility crashes. That's why our team moved to the Autodesk Infraworks 3D BIM platform. This gives us real-time parametric cross-sections, dynamic earthwork updates whenever we modify the design, and visual clash detections across those complex subsurface layers. By feeding high-resolution elevation models directly into Infraworks, our process shifts from reactive troubleshooting to proactive, parameter-driven optimization.
Very good day, I bet to our panel. My name is Sungai and I will present on our proposed solution. So our group has designed a 5-kilometer greenfield industrial bypass to solve our traffic crisis. So when planning the route, we completely rejected massive cloverleaf or stack interchanges because they require too much land and would disrupt local villages, rail lines, and also nearby rivers. While smaller diamond or trumpet designs could work geometrically, they aren't long enough to keep heavy cargo trucks separate from local neighborhoods. Instead, our 5-kilometer bypass safely redirects heavy trucks away from residential areas in Bandar Sungai Buaya and sends them straight to the Serendah industrial zone and upcoming ECRL terminal. To make sure the road is safe and efficient, our design strictly follows the GAR standards. It features a 4-lane dual carriageway with a safe speed limit of 60 to 80 km per hour, and we have set the lane width to be 3.65 meters to prevent side sweep accidents. Kept hill slopes under 6%, so heavy trucks do not lose speed going uphill, and added a 2-meter raised central median to completely eliminate head-on collisions. To bring this design to life safely, we use autonomous Infraworks to optimize our earthworks and design parameters. We stabilize all roadside slopes at a safe 1:2 ratio, and to prevent water damage, we place concrete drainage ditches along the top of hills, cut to channel rainwater away from the road. In areas with soft muddy ground, we plan to dig out the weak topsoil and replace it with a strong subbase wrapped in high-strength geosynthetic fabric sheets, protecting the road from future-heavy truck ruts.
Good day everyone, I'm Afiq. Today I will take you through the technical design of the Hulu Selangor Bypass Digital Twin. We look at how we integrate JKR compliant safety asset into the road corridor to protect drivers and heavy vehicle traffic. We focus on three main elements. Number one, runoff containment. We place semi-rigid steel W-beam guardrails along all field sections where the embankment drops exceed 3 meters. This keeps vehicles from veering off the road. Number two, night navigation. We map out high-intensity reflective signs positioned exactly at optimum stopping sight distance, keeping heavy freight braking needs in mind. Number three, delineation. For lane discipline, the model includes high-contrast thermoplastic markings mixed with retro-reflective glass beads. This ensures the lane lines stay highly visible at night and during heavy rains. Moving to the next slide, we address long-term environmental protection and safe night operations. Number one, smart lighting. On the left, we implemented high-pressure smart LED lights on double arm posts along the 2-meter central median. The spacing is fully optimized to provide uniform lighting across all lanes while eliminating dangerous glare for oncoming drivers. Number two, hydrological spec. On the right, we solve water drainage issue. We replace all easily clogged 600 mm pipes with large precast concrete box culvert. Our simulation showed this culvert can easily handle a 50-year flood. We also added reinforced concrete head wall and ring wall to stop slope erosion and keep water from soaking into the road subgrade. Finally, this slide shows the intersection where the bypass interface with urban areas. Intersections are high-risk zones, so we use the digital twin to lower friction between freight truck and local commuters. Geometric widening, we widen the intersection and optimize the turning angle specifically for massive WP20 interstate trailers. This prevents them from spilling into other lanes while turning. Number two, urban furniture protection. We place heavy steel safety bollards to physically separate heavy truck turning paths from pedestrian waiting areas. Number three, transit integration. Lastly, we position bus stop and utility conduits completely outside the truck kinetic sweep zone, keeping commuters perfectly safe. To wrap up, this digital twin ensures our highway design is JKR compliant, freight resilient, and safe for the public. By testing everything digitally first, we guarantee a smarter and safer highway.
Next, we will discuss how to propose infrastructure project directly contributes to three key United Nations Sustainable Development Goals, specifically SDG 9, SDG 11, and SDG 13. We have made each engineering action to specific SDG to clearly demonstrate the broader micro-level impact of this project. Let's begin with SDG 9. This is not just a design tool, it is a permanent data framework that minimizes material waste during constructions, optimize earthworks, and support lifecycle asset management for decades to come. This directly supports SDG 9 by building resilient infrastructure and fostering innovations. Next, SDG 11. Here, our aim is to divert massive commercial fleets into a dedicated 5 km bypass. By doing this, we actively siphon heavy emissions and 84 decibels of noise pollution away from the residential area of the Buaya. They significantly improve local air quality and drastically reduce accidents, making the community safer, healthier, and more sustainable. And finally, we will talk about SDG 13, which is climate actions. For this goal, we are upgrading the drainage system to 50 years return period box culverts and stabilizing slopes along the corridor. At the same time, it protects the Sungai tributary ecosystems, vegetation and sedimentation, preserving water quality and aquatic life. For this final slide, we present the project synthesis and outline the subsequent technical phase that will follow the current design stage. We have identified 3 critical technical phases to advance the project from design to construction. Phase 1, which is microscope traffic validations. In this phase, we will export the digital drainage networks into PDV VSIMS, a high-fidelity traffic simulation software. This allows us to rigorously simulate changing behaviors and analyze peak hours visuals delay profiles. The goal is to validate that our geometric design performs optimally under real-world traffic conditions before any physical construction begins. Phase 2, geotechnical borehole extractions. Next, we will execute deep subsurface drilling, specifically in the low-lying alluvial clay segment along the alignment. This is essential to lock in
versus consolidation rates, and finalize the foundation specifications. Without this data, we cannot guarantee the long-term stability of the structure. And the third phase is formal environmental impact assessment, EIA. Finally, we will finalize the legal environmental frameworks through a formal EIA. This phase is critical because it allows us to design targeted sediments containment and runoff control plans prior to breaking ground. That's all from us. Thank you for your attention.